Hey everyone. Welcome to my video today. Today we're going to talk, this is my very first AP Physics video, and we're actually not even really talking about physics. We're going to talk about math. Um, we're going to talk today about derivatives, or as I like to think of them, fancy division. Um, and so we're going to look a little bit at what derivatives are, how we use calculus to solve for derivatives. And then once you know how to do a derivative, what does that let us do in physical problems? All right, let's get started. So, one of the very first things that you learned when you started doing like decent math was slope. So, you would look at a graph, and on that graph, you might have a line. And we would ask, what do we know about the slope of that line? And you probably learned that slope is rise over run. So it's the difference in the y coordinates divided by the difference in the x coordinates between any 2 points on that line. And of course, you probably also learned something like slope-intercept form, where a line can be written as y equals slope times x coordinate plus the y-intercept, or maybe even point slope form, right? And at some point, you may have wondered, but what if it's not a line? Because right around the same time that we start to learn this, we start to think about other interesting graphs, like ones that look like this. Could we find the slope of a curve? Well, it turns out that that kind of simple way of thinking isn't quite what we need to find the slope of a curve, but it's really, really close. And so that is what calculus sets out to answer when we start doing derivatives. Because really, a derivative is just the slope of a function. And yes, that function can be a line, but it can also be a curve. So let's think then about how do we mathematically do that? It's sort of similar to our math with the linear slope over here. So at first we think about like, well, what if we have 2 points and we just find the slope between those 2 points? And that will give a good approximation depending on how close the 2 points are. The closer the 2 points are, the better the approximation will be. So you can see here, if we had done those first 2 points, we would have a slope of a line that looks kind of like this. But if we do these two lines that are, or these two dots that are really close together, then the slope of our line is going to look something like this. And so what Newton ultimately thought about was, well, what if we make those 2 points infinitely close together? Then what would happen? And the answer is that you would have the slope of the line at a single point. And that's actually mathematically how we solve this. So I'm going to do a fairly straightforward mathematical um, proof for this graph, which is y equals x squared. Oh. Um, if you are in calculus, obviously you will have done this for other graphs, and that's great. But today I'm just doing y equals x squared. So we are going to look at point here that has some x value and some y value. And then we're going to look at another point that is infinitely close. So we're going to say it's like x plus h. And of course, it also has a y value. We'll call that f of x plus h. And we're basically wondering, as h approaches 0, what does the slope between those 2 points approach? Okay, that's what we're going to be trying to look for here. If you think that sounds like we need to use a limit, you're right. So let's think about what the expression for slope would be, kind of based on this formula up here. It would be f of x plus h minus f of x over x plus h minus x. And what we're wanting is the limit of that as h approaches 0. Okay, let's go ahead and substitute in, since we know that this function is y equals x squared. Up top, we're going to have x plus h quantity squared minus x squared over, and you'll see what happens. Well, the x and the minus x cancel, get h down here on the bottom. Now, that might freak you out because, like, we know h is going to 0 and we can't divide by 0. But in calculus, generally speaking, like, wait till the end before you get too freaked out by a divide by 0, because a lot of times things are going to cancel. And that's what's going to happen here. All right. We can FOIL out the top. So we'll get x squared plus 2xh plus h squared here, minus x squared all over h. Okay, we get a positive x squared and negative x squared, so those are going to also subtract away. So this gives us the limit as h approaches 0 of 2xh plus h squared over h. And what we see there is that every term has h in it. So we can factor out an h on top. Which means that's going to cancel with the h on bottom. And now we get the limit as h approaches 0 of 2x plus h, which is just 2x. And that is our answer. So anywhere along that curve, the slope of the curve is just 2 times its x coordinate. So down here at x equals 1, that would give us a slope of 2. But up here at like x equals 4, that would give us a slope of 8. And that makes sense, right? It starts with a low slope and it goes higher, so that will work. And it also is clear to us that, like, at 0, it has 0 slope, right? It's horizontal. And so that works for us as well. So if you were in calculus class, you would do a lot of this and you would be proving to yourself a lot of the different slopes. Luckily in physics, and specifically on the AP Physics exam, they give you a whole list of how to find the slopes of different functions. And so there are a couple rules that you're going to want to keep in mind. And the biggest one for us is about these particular quadratics, quartics, etc. And so it's a power rule. So something that you should know is that if you ever have a function that looks like ax to the b, where a and b are both numbers, then the derivative of that function, you pull down the b in front, and then you subtract 1 from the b up here. So if I have something like 3x squared, I pull down the 2 to get 6, and then I subtract 1. So 6x to the first, or 6x. Okay. So that's a little bit about the mechanics of derivatives. As I mentioned on your AP Physics sheet, you have a lot of derivatives defined for you. And so if you have a function, a cosine, an exponential, a polynomial like this one, you should be able to figure out what the derivative is just from what's on that sheet. Hopefully you're also in calculus, and those are things you've also been practicing and are able to use pretty easily. So let's think about applications. And some of the biggest applications that we see are in motion. So if we think about a velocity versus time graph, and let's say our velocity versus time graph looks like this. When we think about the position, velocity, and acceleration concepts, something that we learn is that they are very closely related to each other. And they're, in fact, related through this exact relationship. Because your acceleration is how much your velocity changes each second. And if you were able to take an algebra-based physics class before you took a calculus-based one, you probably looked at mostly linear velocity graphs, and you thought of acceleration as the slope of those velocity graphs. That's still true. It's just that now we have a fancier definition for slope, and therefore we are able to make it work for curves as well as lines. And so really what that means is that the acceleration is just the derivative of velocity. And similarly, velocity is how far you travel each second, right? So velocity is just the derivative of position. And that means that acceleration is something that we call the second derivative of position, which means we take the derivative of position to get velocity, and then we take it again to get acceleration. So all of motion is full of derivatives, and using them to find the slope. But I think there's some other places that people get surprised by derivatives popping up, because truly, what is a derivative except for like fancy division, right? We're just looking at the difference in one thing divided by the difference in another. And so, yes, one place we see it a lot is motion, but we kind of see it all over physics. So for instance, let's think of a pretty straightforward equation. We know that the absolute value of the force of a spring is kx, right? So it's related to how far we stretch it and the spring constant. Well, that means that the spring constant could be thought of as just force over extension. So if I had a graph of force and extension, then I could use a derivative to find what the spring constant is. Now, most of the time with ideal springs, those are going to be linear. So it's really a slope, not so much as advanced as a derivative. But it could be, right? So basically anything you can write as one thing divided by another, you could think of as a derivative of this thing with respect to that thing. All right. I'm sure derivatives are going to pop up in a lot of other videos, so I'll let this one stop here. But that is our basics of derivatives and how we're going to use them in physics. Thanks.